Assalamu alaikum everyone. So today we're going to be starting off the second part of this chapter, which is errors and uncertainties. The learning objectives are understand and explain the effects of systematic errors, including zero errors and random errors in measurements, understand the distinction between precision and accuracy, assess the uncertainty in derived quantity by simple addition of absolute or percentage uncertainties. So we're going to be covering these in this particular video. Errors and uncertainties, we need to know why do errors arise. So there are a few reasons why errors arise. There because of the limitations of the observer's measuring skills. It means that the observer's measuring skills might be faulty or there might be some limitations in them. Then the second reason is that the limitations of the measuring instrument used. So there might be an error in the instrument itself. It might be faulty. So this is the second reason. And the third reason is the limitations due to the continuous variation in the external environmental conditions. So this is because the external environmental conditions might keep changing, the speed of air, etc. It might keep changing, and this is why there might be an error in the reading that we're recording. So these are the three reasons why errors might arise. Now there are two different types of errors. There are random errors and there are systematic errors. So what exactly are random errors? Random errors are errors with a variable sign, which means that basically it's like there is not only one overstated or an understated result. It can be both. So there are errors with a variable sign. It's not always a positive result or a negative result, not always overstated or understated. It can be both. So there are errors with the variable sign. Now second thing is that random errors can be minimized by repeating trials and taking average. What does it exactly mean is that we repeat the experiment over and over again and then we take an average of the reading we're getting. This is one way to minimize the random errors. Some example of random errors would be speed of sound calculated if the direction of wind continuously keeps changing. Now, how is this error arising? This error is arising due to continuous variation in the external environmental conditions, right? Because the direction of wind is continuously changing. Therefore, different speed of sound would be calculated in this experiment. Secondly, the second example is boiling point of a liquid if atmospheric pressure keeps changing. Because we know that the boiling point of a substance changes according to the atmospheric pressure, right? So this is also an error which is a result of the continuous variation in the external environmental conditions. Because since the atmospheric pressure is changing, the boiling point that we obtain through a specific experiment would also be different. Therefore, this is an example of a random error. Thirdly, the third example is the diameter of wire if variable pressure is applied by the micrometer screw gauge. So, which form of error is this? This is a random error and this is arising because of the limitation of observer's measuring skills. Why? Because the observer is applying different pressure on the wire using the micrometer screw gauge, due to which different readings of the diameter of the wire are being obtained, right? So these are few examples of random errors. Now if we basically plot a graph of random errors, we know that the scatter of points would be on either side of the best fit, which would indicate the presence of random errors, right? Because we at the beginning learned that random errors are errors with a variable sign. So it can be overstated and understated both. So the scatter of points would be on either side of the line of best fit and not only on one side. So this is what a random error is. Now moving on to systematic errors. Systematic errors have no variable sign, which means that systematic errors either cause an overstated result or an understated result, but never both. This is the difference between the random and systematic errors. We learned that in random errors, the errors were of a variable sign. So they could result in an understated or an overstated result both. But systematic errors only have either an overstated result or an understated result. So there is no variable sign. Secondly, they cannot be eliminated by taking repeated trials, but it can be eliminated by modifying technique. What does it mean? Earlier we learned in random errors that it could be minimized. They could be minimized by repeating the trials and taking average, which meant that random errors could not be eliminated. They could not be completely removed, because obviously you see if there's a change in the external environment, if we repeat the trials, the change or the variation would still exist. However, the effect of that variation would be reduced because now we have taken a lot of averages and now we have an average reading, right? So it cannot be entirely eliminated because it would still be present, but the effect would be reduced. But in systematic errors, the systematic errors cannot be eliminated by taking repeated trials, but they can be eliminated by modifying techniques. So it means that the systematic errors can be completely eliminated and not just reduced. And how are they completely eliminated? They're not eliminated by taking repeated trials. There would be no effect by taking even if we take a repeated trial. For example, if we have a fault in the measuring instrument that we are using, even if we repeat the trial continuously, the fault would continue to exist. So there would be no effect on the systematic error. However, if we completely change the measuring instrument we are using, or we completely remove the fault from the measuring instrument, only then the systematic error would be completely eliminated, right? So they cannot be eliminated by taking repeated trials, but they can be eliminated by modifying the technique. Now we'll go through a few examples of systematic errors. The first example is a zero error. What is a zero error? A zero error is basically an error in the measuring instrument we are using. For example, a vernier caliper or a micrometer screw gauge, right? So there would be an error in the measuring instrument we are using, and it would either give an overstated result or an understated result, but never both, right? The second example is a faulty stopwatch, because obviously if we have a stopwatch which is either too fast or either too slow, then the measurements in the experiment we are carrying out would always be wrong, right? If it is too fast, then obviously the measurement is wrong. If it is too slow, then again the measurement is wrong. So it cannot be eliminated by repeating the trials, because the stopwatch would still remain faulty. However, if we use a different stopwatch, or if we completely eliminate the fault from the stopwatch, only then the systematic error would be eliminated. Now the third example is ignoring to subtract the background radiation. So sometimes there is a background radiation in certain radioactive processes, right? So if you're counting the activity, for example, and we forget to subtract the background radiation, then the answer that we'd be getting would be different from the actual activity, right? So this is an example of a systematic error, because if we ignore to subtract the value, no matter how many trials we repeat, the error would still exist and would not be eliminated. So the only right way would be subtracting the background radiation, and this is how we can modify our technique in order to eliminate the systematic error. The fourth example is by taking a wrong value. For example, if we take acceleration due to gravity as 10 meter per second instead of we take it as 12 meter per second instead of 10 meter per second, then we're taking a wrong value of acceleration due to gravity, and so in all our calculations we'll be getting a different answer from the actual answer, because we're using a wrong technique. So no matter how many calculations we repeat, we'll still be getting a wrong answer. So the only right way would be to take the correct value of acceleration due to gravity, right? So in this way, by correcting the value of the acceleration due to gravity that we're using, in that way we can actually eliminate the error by modifying the technique. Now if we plot a graph of a systematic error, we would know that we'd see that the graph basically fails to pass through the origin, right? So the line is failing to pass through the origin, which shows that there is the presence of an error. The gradient is not affected, but the intercept is affected, because all the readings are shifted by a constant value. We know that the systematic error is not of a variable sign, it is either overstated or understated, right? So the gradient would not be affected because the sign is not variable. However, the intercept would be affected. Why? Because it is either giving an overstated value or an understated value. So according to that, the intercept would be affected. So this graph would be a geometrical evidence of systematic errors, because A, the graph is not passing through the origin, which shows that the systematic error is present, and secondly, the gradient of the line is same, which shows that there is no variable sign. However, since the intercept is being affected, we know that there is either an overstated result or an understated result. Therefore, it confirms the presence of a systematic error. So this graph is a geometrical evidence of systematic errors. Now moving on to accuracy and precision. So accuracy is basically dependent on how close the value is to the actual value, right? And precision, however, basically means it depends upon the spread of values. So if the spread of the values is narrower, it means that the values are more precise. So we'll do an example here. An example is that the true value for acceleration due to gravity is 9.8 meter per second, right? 9.8 meter per second square, right? So if we carry out an experiment 1 and we obtain the values of acceleration due to gravity as 9.6 meter per second square, 9.7 meter per second square, 9.8 meter per second square, 9.9 meter per second square, and 10 meter per second square, we know that this experiment is basically accurate. Why is it accurate? Because the average of all the values that we have present here is 9.8, right? Which means that they're close to the true value, which actually confirms that the experiment 1 is accurate. And how do we check for its precision is, right, how we look at the spread of distribution. Since 9.6 to 10 is basically a narrow spread, so we can confirm that experiment 1 is actually precise as well. So experiment 1 is both precise and accurate. Now moving on to experiment 2, the values we obtained are 9.2, 9.6, 9.8, 10 and 10.4. Now if we take an average of the values of 9.2, 9.6, 9.8, 10 and 10.4, we will get that the average is equal to 9.8, which means that experiment 2 values are also accurate because they're close to the true value. However, if you look at the spread of the distribution, it's starting from 9.2 and ending at 10.4. So the spread of distribution is pretty broad and not narrow. So it means that it is accurate but not precise. Moving on to experiment 3, the values are 1, 1.1, 1.2, 0.9 and 0.8. Since the average is not equal to 9.8, the average of experiment 3 would be around 1 meter per second, right? So it is far away from 9.8 meter per second, which means that it is not accurate at all. But if we look at the spread of distribution, it's starting from 1 and it is it's starting from 0.8 and it's ending at 1.2, right? So the spread of distribution is pretty narrow, which means that experiment 3 is precise but not accurate. Now moving on to experiment 4, the values are 1, 3, 7, 11 and 6, right? So if we take an average of experiment 4, the average would be equal to 5.6, which means that experiment 4's values are not accurate at all. And if we look at the spread of distribution, it's starting from 1 and ending at 11, which means that the spread of distribution is pretty broad, which means that it is neither accurate and nor precise. Now moving on, basically, how do we know that the value is more precise or less precise? So when there is low fluctuation in the data points, which means when there is low variance, then the value is more precise, which means there is a narrow spread of distribution. Whereas when there is a high fluctuation in the data points, which means there is a high variance, which means there is a broader spread of distribution, it means that the value is less precise. Now moving on to the geometrical representation of accuracy and precision, we've been given 4 graphs here, A, B, C and D. So if we look at A, B, C and D, in experiment 1, there is low accuracy and high precision. Why? It is because the true value is far towards the left from the mean, so the mean is not on the true value. It means that it is not accurate. However, it is precise because the spread of distribution is very narrow. Moving on to experiment B, it is both precise and accurate. So there is high accuracy and high precision. Why? Because the mean is on the true value. It means that the value is close to the true value, therefore it is very accurate, and it is precise as well because the spread of distribution is very narrow, because we have obtained a very narrow peak, right? So the experiment B is both precise and accurate. Moving on to experiment C, we know that the mean is not on the true value. The mean is not on the true value, so it is not close to the true value, therefore it is not accurate, and the precision is low as well because the spread of distribution is very broad and not narrow. So there is low accuracy and low precision. Moving on to experiment D, in this graph the mean is on the true value, which means that there is high accuracy because the value is close to the true value. However, since the spread of distribution is very wide and it is not narrow, it means there is low precision. So there is high accuracy and low precision in this graph. So we basically need to keep in mind 2 points. Number 1, for accuracy, the peak of distribution will be at the true value, because we see whenever the graph is accurate, the peak is always on the true value, right? So for accuracy, peak of the distribution will be at the true value. And the second point is that precision is the spread of distribution. The narrower the distribution, the more precise it is. So we've seen in these graphs as well. So we just need to remember these 2 points. Now we'll be learning about how to code physical quantities, right? For example, if we have a value of around 25 centimeter, let's say, and there is a possibility of an error of around 0.5 centimeter. So the value of 25 is basically greater than or equal to 24.5 centimeter and less than equals to 25.5 centimeter, right? So we'll always quote it in a way that L is equals to 25 plus minus 0.5, because the 25 here would indicate the true value or the actual value, and we also call it the absolute value, whereas the plus minus 0.5 would basically indicate the absolute uncertainty, and we also call it absolute error. So we always quote it in a way that L is equals to x plus minus change in x. The x here represents the true value, whereas the change in x basically represents the absolute uncertainty, as we saw earlier how 25 was quoted as 25 plus minus 0.5 centimeter. Right. Moving on to fractional uncertainty or fractional error. So what is the fractional uncertainty or fractional error? To find the fractional uncertainty, we will take change in x upon x. For example, above we were given that 0.5 was the absolute uncertainty, right? So we'll take it as 0.5 upon 25. Basically, the 0.5 here would be the absolute uncertainty and x would be the true value or the absolute value. So, in order to find the fractional uncertainty, it is always the absolute uncertainty upon the true value. Since we took 0.5, which was the absolute uncertainty, upon 25, which was the true value. So this is how we find the fractional uncertainty or fractional error. Now, in order to find the percentage uncertainty or percentage error, we need to take the fraction of fractional uncertainty and then we multiply it by 100. For example, we write it as absolute uncertainty upon the true value multiplied by 100. An example is 0.5, which was the absolute uncertainty, upon 25, which was the true value, and then we multiplied it by 100 in order to obtain the percentage uncertainty, right? So, percentage error or percentage uncertainty is always the product of the fractional error into 100. As we saw, the fractional error was found by dividing the absolute error by the true value. So we take the fractional error and then we multiply it by 100 in order to find the percentage error or the percentage uncertainty. Now, moving on, there are basically 2 laws about how to write true values with their absolute errors. Right? So rule number 1 is basically all absolute errors or absolute uncertainties must be quoted correct to one significant figure. So we need to ensure that we write our absolute error correct to one significant figure. As we saw above, we have 25 plus minus 0.5 centimeter, right? So 0.5 was our absolute error, and we ensured that we can see that 0.5 is quoted correct to one significant figure only, right? Because 0.5 is one significant figure. Now rule number 2 is basically the true value and the absolute error must be consistent in terms of decimal places. In case where absolute uncertainty at one significant figure has no decimal place, then make sure that the true value is rounded off to the same place value as the uncertainty. So we need to ensure that the true value and the absolute error must be consistent in terms of decimal places. As we can see that it is 25.0 and it is 0.5. So they're all written correct to one decimal place, right? And similarly, if there is a case where the absolute uncertainty at one significant figure has no decimal place, so what we basically do, if there is no decimal place present in the absolute uncertainty, then what we do is that we make sure that the true value is rounded off to the same place value as the uncertainty. For example, if the absolute uncertainty was only 5, then we would have rounded off 25 to the same 25.0 to the same place value as the absolute uncertainty, so it would also become 25, right? Because they're both rounded off to the same place value now. So these are the two rules which we need to remember when we're writing the physical quantities. Now moving on, here are a few examples of significant figures. So A is 0.01, we know it is correct to one significant figure. Now there is B, which is 0.010, which is correct to two significant figures. How do we know that they're equal to one significant or two significant figures? Is because there are certain rules for significant figures. The first rule is that all non-zero digits are significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9, they're all significant. The second one is all zeros between two non-zero digits are significant. So 5004, for example, which is equal to 4 significant figures. Why? Because all the zeros between the two non-zero digits, the two non-zero digits here are 5 and 4, and all the zeros in between would also be significant, right? So 5004 is equal to 4 significant figures. And the third one is that all zeros to the right of both a number and a decimal in a decimal number are significant. For example, there is a value of 3.4000. So we know that this is equal to 5 significant figure. Why? Because all zeros to the right of the number and the decimal are significant. So all the zeros which are to the right of 3.4 are significant, right? This is how these are some basic rules for significant figures. So I'm pretty sure that you can figure out how significant figures each of these values is equal to. So you can pause the video here and you can check whether or not you are able to identify the number of significant figures each of these values are equal to. Now moving on to the application of rules. Which rules here are we talking about? We're talking about the two rules that we studied earlier. The two rules which are basically all absolute errors must be quoted correct to one significant figure, and the second rule was that the true value and the absolute error must be consistent in terms of decimal places. In a case where absolute uncertainty at one significant figure has no decimal place, then make sure that the true value is rounded off to the same place value as the uncertainty. So here we have certain examples. We'll take the first example, which is 7.627 plus minus 0.38. So when we're quoting this value, we're going to ensure that the absolute uncertainty is written correct to one significant figure only, right? So 0.38 would become 0.4. Why? Because 38 would be rounded off to 4 in order to make sure it is written correct to one significant figure only. And the second thing that we're going to ensure is that the 7.627 must be consistent in terms of decimal places with the 0.4. So since 0.4, the absolute error is correct to one decimal place, so we'll ensure that this true value would also be written correct to one decimal place only. So we'll write it as 7.6 instead of 7.627. The same goes for the subsequent values that are written over here. So after 1 we're going to come to 7, and in 7 we can see that it is 672.67 plus minus 2367.81. So when we're writing the absolute error, it should be correct to one significant figure only. So we'll write it as 2000 instead of 2367.81. So since it's correct to one significant figure, it's going to become 2000. And since we need to ensure that the absolute error and the true value are consistent in terms of decimal places, but in 2000 we know that there are no decimal places, so we know that we have to make sure that the value is rounded off to the same place value as the uncertainty. So since the uncertainty is written in terms of 1000, so we are going to round off the true value to the same place value as the uncertainty, and so 77,627 is gonna get rounded off to 78,000. So the answer is gonna be 78,000 plus minus 2000. Now all of the remaining examples are very easy. You may once again pause the video and have a look at these to ensure that your concept about the rules and the application of rules is clear. Now we'll be moving on to the addition of physical quantities, right? So for example, we have A, which is 18.5 plus minus 0.5 meter, and we have B, which is 12.5 plus minus 0.5 meter. Now we have to find the value of C, and C is basically A plus B along with its uncertainty, right? So we need to basically add A and B in order to find C. So when we are quoting C, we're basically going to add the true values of A and B. 18.5 plus 12.5 is going to become 31. And while we're quoting the uncertainty, we're again going to add the uncertainties. So it's going to become 0.5 plus 0.5 will be equal to 1. So C will be equal to 31 plus minus 1 meter, right? And when we are subtracting the physical quantities, we have A again 18.5 plus minus 0.5 and B is 12.5 plus minus 0.5. D is basically A minus B. So here we have to subtract B from A, right? So when we're quoting D, we're going to write it in a way that the true values are going to be subtracted. However, the uncertainties are again going to be added. So whenever physical quantities are added or subtracted, their absolute errors are always added. We need to know this. When we were adding the physical quantities, we added the true values, but we added the uncertainty as well. But when we were subtracting the physical quantities, we subtracted the true values, but we still added the absolute uncertainty. So the rule is that whenever physical quantities are added or subtracted, their absolute errors are always added. Now here's another question. It says U is equals to 20 meter per second, V is equals to 80 meter per second. Both the values are are accurate to 1 meter per second, which means that both the values would be written as plus minus 1, right? And we have to find the fractional error in change in velocity. So what is velocity? Velocity is change in velocity would be final velocity minus the initial velocity, right? V is the final velocity and U is the initial velocity. So change in velocity would be V minus U. Now the values of V and U were 20 and 80 respectively, right? For V and U were 80 and 20 respectively, right? So when we're writing the change in velocity, we're gonna subtract U from V. So we're gonna subtract 20 from 80, so that's gonna become 60. And when we're writing their absolute uncertainty, as we learned earlier that the absolute uncertainty is always added, so we add their uncertainties. So 1 plus 1 is gonna become 2, so it will be written as 60 plus minus 2, because the true value was subtracted but the absolute uncertainty was added, so it's written as 60 plus minus 2. When we are finding their fractional error, we earlier learned that the formula of fractional error was the absolute error upon the true value, right? So here we know that the absolute error in change in V is 2 and the true value is 60. So we're gonna write it as 2 upon 60. So the answer is 1 upon 30. So the fractional error is 1 upon 30. And when we're finding the percentage error in change in V, we also learned that fractional error multiplied by 100 is a percentage error, right? So we're gonna write it as a fractional error 1 upon 30 multiplied by 100, so that becomes 3.33%, which is the percentage error. Now we'll be moving on to the multiplication of physical quantities. When we're multiplying the physical quantities, the true values are multiplied, but the fractional errors and the percentage errors are added. Earlier in addition and subtraction, the absolute errors were added. However, in multiplication and division, the fractional error or percentage errors are added and not the absolute errors. An example would be, we have length of 6 plus minus 0.5 centimeter and breadth is 5 plus minus 0.2 centimeter, right? We have to calculate the area along with its uncertainty. So we know that area is length into breadth, right? So we'll be multiplying 6 by 5. We'll be multiplying the length by the breadth. So 6 would be multiplied by 5. So the answer becomes 30 centimeters square, which is the true value. However, when we'll be quoting it, we have multiplied the true values. So we'll write 30 as it is. But when you're writing it as plus minus, we'll be actually quoting it with the fractional we'll actually be adding the fractional errors, right? So the fractional error in area would be written as the absolute error upon the true value of A is equals to the absolute error of length upon the true value of length plus the absolute error of breadth upon the true value of breadth. So in this way, we'll find the fractional error in the area, right? Because we see that we have written the fractional error in area is equals to the fractional error in L plus the fractional error in B. So we're gonna be adding both the fractional errors in A and B, and then we're gonna be multiplying it by the true value of A in order to find the absolute error in A, right? And then when we find the absolute error in A, which is basically 3.7 centimeters square, we're gonna be writing it as 30 plus minus 4 centimeters square. Why did we round off 3.7 to 4? That was because we know that we have to write the absolute error always correct to one significant figure. So 3.7 was rounded off to 4, and the answer becomes 30 plus minus 4. So this is how it works. Now moving on to another example of the multiplication, there is x is equals to 36 plus minus 0.2 meter, y is equals to 14.5 plus minus 0.1 meter, and z is equals to 3.26 plus minus 0.01 meter. So s is equals to x cube, y, and z square. So we basically have to find s, right? And s is the product of x cube, y, and z square. So we'll write s, instead of x we'll write 36, instead of y we'll write 14.5, and instead of z we'll write 3.26, and we'll write their powers as it is, right? So when we actually multiply it with their correct powers, the answer would become 7189698.931, which will be the true value. So we can write it as 7.189698 into 10 to the power 6 when we're writing it in the standard form, right? So this will be the true value. However, when we're writing the absolute error, we need to multiply their fractional uncertainties, right? So when we're multiplying their we have to add their fractional uncertainties, right, in order to find the absolute error. So we'll write it as the absolute error in s upon the true value of s is equals to the absolute error in x upon the true value of x plus the absolute error in x again upon the true value of x plus the absolute error in x upon the true value of x. Why have we taken it 3 times? We have taken it 3 times because it was to the power of 3, right? X was to the power of 3, so we took it 3 times. Then we added with the absolute error in y upon the true value of y, and then we added with the absolute error in z upon the true value of z plus absolute error in z upon the true value of z. Why have we taken it twice? Because z was to the power of 2, right? So when we write it, we can actually basically just multiply the fractional errors in x by 3 and the fractional error in z by 2, because we always multiply the power with the fractional error in one of the x, right? So the fractional error in x was change in x upon x, right? The absolute error upon x, right? So we take this and we multiply it by 3, and similarly we take the absolute error in z upon true value of z and multiply it by 2. This is how we write it, and then we solve it. We basically add all of these values, and then we multiply it by the true value of s. When we multiply it by the true value of s, we are able to find the absolute error in s. So the absolute error in s basically becomes 0.2135 into 10 raised to the power 6. So we write as we basically know that s was the true value of s was 7.2 into 10 raised to the power of 6, right? So we'll take 10 raised to the power 6 as common as it's present in both, and then inside the bracket we only write 7.2 plus minus 0.2. Why have we taken it as 0.2? This is because the absolute error is always written correct to one significant figures, right? So this is the rule that if z is equals to x to the power of m and y to the power of n, then fractional uncertainty in z is as follows. And you can see it here. The absolute error in z upon z is equals to m. What was m? M was the power of x, right? And then we multiply the power by the absolute error upon the true value of x, and we added with n. N was the power of 5 multiplied by the absolute error in y upon the true value of y. And this is how we're able to find the fractional uncertainty in z. And then after we're done finding the fractional uncertainty in z, we multiply it by the true value of z in order to find the absolute error in z. Now moving on to the division of physical quantities. So what basically happens in the division of physical quantities is that the true values are divided, whereas the fractional errors are always added. For example, we have distance that is 40 plus minus 0.1 meter and the time is 2.5 plus minus 0.05 seconds, right? So we have to calculate the speed along with its uncertainty. We know that the formula of speed is distance upon time, right? And the speed, so here we are going to divide the distance by the time, right? So we're just gonna take the value of distance, which was 40, and we're gonna divide it by time, which is 2.5, in order to get the speed, which is 16 meter per second. So what we've done here is, when we're dividing the physical quantities, we've normally divided the true values. However, what do we do with the fractional errors is that we're gonna be adding the fractional errors. How? We basically took the absolute uncertainty in S upon the true value of S is equal to the absolute uncertainty in D upon the true value of D, and we added it with the absolute uncertainty in T upon the true value of T. So what we're basically doing here is we're adding the fractional uncertainty or the fractional errors, right? So we divide. How do we find the fractional error? Fractional error is always the absolute error upon the true value. So absolute error in distance was 0.1 upon true value, which is 40. So 0.1 upon 40 plus 0.05 upon 2.5, right? So the absolute error in S upon the true value of S. What was the true value of S? It was 16 meter per second, right? So we write it this way, and what we basically do is that after adding the fractional errors, we multiply it by the true value, which was 16, the true value of S, which is 16, in order to find the absolute error in S. In this way, we'll find the absolute error to be 0.36 meter per second. So we'll find that the speed is 16.0 plus minus 0.4 meter per second. Why do we write it as 0.4? It is because the absolute error is always written correct to one significant figure, right? So the 0.36 would be rounded off to 0.4 and it would be written as 0.4. So 16 plus minus 0.4 meter per second. So the rule is, when physical quantities are multiplied or divided, the fractional uncertainties are always added. Now we'll be doing a question regarding the division of physical quantities. So it says, if z is equals to x raised to the power of m divided by y raised to the power of n, then the fractional uncertainty in z would be as follows. What would it be? It is basically the absolute error in z upon the true value of z is equals to m multiply by the absolute error in x upon the true value of x. So what we've done here, we've basically multiplied the power, which was m, the power of x, which was m, with the fractional error in x. So the power will be multiplied by the fractional error in this situation, plus n, which was the power of y, is multiplied by the fractional error in y. So it is m multiplied the fractional error in x plus n multiplied by the fractional error in y. And in this way, after adding these fractional errors, we'll be multiplying it by the true value of z in order to find the absolute uncertainty in z. So the question says, if the length is equals to 5 plus minus 0.5 centimeter and the height is basically 6 plus minus 0.5 centimeter and the cuboid has a square base L, we need to find the volume along with the uncertainty. So we know that the volume of the cuboid is basically length into breadth into height, right? However, we know that this cuboid has a square base, so we'll take L square instead of the breadth, and we'll take L square, so it will be written as V is equals to L square into height. So what is your length? We have the length as 5 centimeter, right? So we'll write the volume as 5 square multiplied by 6, which was the height, right? So normally, as we've normally done before as well, we'll multiply it and we'll get 150 centimeter cube, which is the true value. Why is it the true value? Because we're simply multiplying the true values here. However, in order to find the fractional uncertainty in this question, what we're going to be doing here is that we're going to be adding the fractional errors. So how do we do that? We take the change in we take the absolute error in v upon the true value in v, and is equal to 2. What was 2? 2 was the power of L, right? So we multiply 2 by the by the fractional error L, and we add it with the fractional error in H, right? So in this way we're going to be adding the uncertainties, and then we're going to be multiplying it by 150, which is the true value of V, in order to get the absolute error in V, which is 42.5 centimeter cube. So we'd be writing it as V is equals to 150 plus minus 40 centimeter cube. Why have we taken it as 40? Because absolute error is always written correct to one significant figure, right? So we're going to be rounding off 42.5 to 40. So this is it. This was a question about the multiplication of fractional uncertainties. So with this, we come to the end of the second part, which is errors and uncertainties. Now stay tuned for the third part of this chapter, which is scalars and vectors, which I'll be covering in the next video. Bye bye.